Yeah.
So let us wait for a few minutes. Yeah.
Yes, yes. Yeah, you can just tell me when you to start.
Yeah.
I think Professor.
Yeah, Mosumi.
Yes.
You can actually, I can tell a little bit about you. I mean,
oh.
Maybe you can tell. I'm just getting a call.
Yeah, no problem.
Mosumi does this density matrix. Renormalization group, which has a very close connection with, quantum computation kind of thing, because they rely on entanglement.
Yes. Actually, I plan to give a talk which actually basically helps the students, because from the basics, I would like to give a talk because I'm thinking in July 16th, right? You just fixed on July 16th on my talk.
I think July 16th, right?
Yes, I think so.
Yeah, July 16th.
Yeah, I hope that I'd like to give you some basic about the DMRG so the students can actually help from that. So let me see. Okay. Thank you.
So Ashwini, morning session was very well attended, close to 200 people.
I think Ashwini is muted. Yeah. It was, I was surprised, about 180 people I saw.
Yes.
It was a good session. I enjoyed, I learned. And So you are in the middle of the school, is it?
Yeah, little more than middle, we have around 18 days we have finished.
Okay.
So another 15 more days to go.
Okay, yeah.
But it has been quite nice because most of the speakers have talked to basics.
Good. Yeah, do think about coming up with a volume on.
Actually, I'll come and talk to you, and Ashwini is also there. So that's a very good suggestion, because the first one was supported by the academy, all these three academies.
Okay.
So I'll get input from you people before we start. I think it's a very good suggestion.
Yeah.
Mosumi, you can slowly start.
Okay. So let me start then. Good afternoon to all of you. It's been a wonderful session in the morning that we had three talks which are very exciting on quantum chemistry dynamics. So now it's time, my privilege to introduce to you today's speaker in this evening, Dr. Kenji Sugiaski from Osaka City University. A brief introduction about him. He is working as a specially appointed lecturer in the Department of Materials and Molecular Systems in Osaka City University. And his current research of interest includes the development of new algorithms that can be used efficiently on quantum computers. And so that it can be used to calculate the electronic structure, magnetic properties of molecules and material. So that's the reason that we all quantum chemists are eagerly waiting for his talk. They just hopefully that he's going to show us a new algorithm that can be actually fit into quantum computers. So with that, I would like to invite Professor Sugiaski to deliver his lecture. And you have maybe 45 to 50 minutes for your talk. And after that, we will have a question answer session. Over to you, Dr. Sugiaski.
Thank you very much. And thank you very much for your kind introduction. And thank you very much for inviting me to this wonderful summer school. I'm Kenji Sugiaski from Osaka City University. Actually, my background image is my university, which is taken from the official Facebook account of my university. But anyway, let me share my screen. So can you see my slide?
Yes. You can put, yes, a full screen mode. Okay. Okay. We can see.
So today I'm going to talk about quantum chemical calculation and the quantum algorithm known as phase estimation algorithm. My primary occupation is also City University. I have a visiting position in physical quantum engineering research and education, and this is a class in India. First of all, I would like to start by defining what is the quantum chemical calculation. If we define quantum chemical calculation in single sentence, it solves the Schrödinger equation. Schrödinger equation is a fundamental equation of quantum mechanics to disclose electron structure of atom and molecule solution. So quantum chemical calculation can create even unknown compounds or shock-wave reactive intermediates, which can be too shock-wave to isolate. Also, we can calculate the transition structures. So we can calculate, for example, molecule in crystals, host crystals to disclose the stable conformations, or we can use quantum chemical calculation to spectral assignment or disclose the reaction pathways. So before studying the detail of the quantum algorithm, I would like to clarify the motivation why quantum chemical calculation on quantum computers is so important. There are two kinds of answers from the quantum computing community and also from the quantum chemistry community. One answer is, of course, the atom and molecule are quantum mechanical systems, so it can be directly treated by quantum computers. Also, the problem is well defined. I will say in the next few slides, the problem is well defined. Hamiltonian is known. Also, there are many examples of quantum chemical calculation on classical computers. Also, quantum algorithms, exponential faster than classical one, are already known. Actually, the quantum phase estimation one of the quantum algorithm of such exponential speed up is available. Another reason is we expect to achieve quantum advantage with small number of qubits. So basically, if we can treat the, for example, 50 or more qubits with very long coherence time and very high accuracy in control, we can expect the quantum advantage can be realized in the quantum chemistry problems. And also, the answer from chemical community to this question is, one reason is the quantum chemical calculation now one of the fundamental research tools in chemistry. So everyone can use quantum chemical calculations to explore electron structures of atom and molecules. Also, we want to calculate large molecules with very sophisticated methods. Because the quantum chemical calculation is very fundamental, familiar tool, but we have to include several approximations to carry out quantum chemical calculation for large molecules. So sometimes the result of quantum chemical calculation doesn't match to the experimental results. So we want to calculate the molecules with very sophisticated method. But this kind of calculation is very difficult on classical computers. And also, we want to predict the chemical phenomena based on quantum chemical calculation. If we can predict the chemical phenomena, for this can be used to generate a guideline for molecular designs. So this is a Schrödinger equation. This is when, as you can see, H is the Hamiltonian, and psi is a wave function which includes information of spatial distributions and relative orientation of electrons, and E is energy of the system. So In this equation is very simple. Applying Hamiltonian to the wave function, we can obtain the energy. But also, this equation is very simple. But if we apply this simple Schrödinger equation to many electron systems, the equation becomes too complicated to be solved. So we have to introduce some approximation to execute quantum chemical calculations. So why quantum chemical calculations so difficult? Because the electron Hamiltonian includes the interaction between electrons. So electrons move in correlation with each other to avoid collision. So the position of an electron depends on the growth of the other electrons. So it means if we consider very simple motion of particles like this one, but if we think about two correlated motion of two particles, these two correlated motion is quite different because the as you can see, this is this is this term is the Coulomb term, so it is inversely proportional to the electron distance. So these two correlated motion have different electron distance, so the situation is very different. So we have to discriminate because of correlated move of electrons. So considering the n electron molecule, solving the problem of correlated electron is very difficult. So we start from the mean field approximation. So it means we solve the equation of an electron moving in electron cloud formed by n-1 electrons. So mathematically, the wave function is corresponds to approximation of wave function by a single electron configuration or single theta determinant. So this is an example of the Hartree-Fock wave function, and this is the water molecule in SQ3G in minimal basis. And in this case, one electron wave function is the molecular orbital like this one and this one. And this molecular orbitals are expanded by known function known as a basis set. And in the Hartree-Fock calculation, we optimize these molecular orbitals to minimize the energy. But the Hartree-Fock equation, in the Hartree-Fock equation, the wave function, we optimize the orbitals. But orbitals, but the problem equation what we want to solve depends on the orbitals. So we have to perform in self-consistent manner. But if we solve the Hartree-Fock method, it usually covers about 99% or more of total energies. So one can expect Hartree-Fock is enough for to understand chemistry. The answer is absolutely no. Why? Because chemically deal with difference in the order of few kilocalories per mole usually. And this is an example of total energy of some molecule of. As you can see, in hydrogen molecule, the total energy is just about minus 1.174 Hartree. And because Hartree-Fock covers about 99%, the rest of the correlation energy is about 7 kilocalories per mole in hydrogen molecule. But if we think about the water molecule, the 1% of total energy becomes about 500. If we think about the fuel ring, the 1% of total energy is very big. but we have to discuss the gap between two electron space or two geometries in a few kilocalories per mole. So we have to include the electron conversion effect that is not included in the Hartree-Fock method. So how to recover the electron conversion effect that is discarded in the Hartree-Fock calculations? One simple approach is to consider the aesthetic conversion from the Hartree-Fock wave function. In this case, this is the Hartree-Fock conversion, and for example, we consider this kind of single electron excitations or two electron excitations or something like that. In this case, the problem to solve this kind of expansion is to determine the expansion question C based on variation principle. And this is the known as the CI method, confirmation interaction method. If we take into account all possible electron configurations, the wave function can be exact within the Hilbert space found by the base set. So this approach is known as a Fuchsia method. However, the number of possible electron configurations increase exponentially against the system size. So if we use the CCPVDC base set, which is for typical basis set used in quantum mechanical calculations, if we apply a Fuchsia calculation by using this CCPVDC base set, for example, in benzene, the number of variables become about more than 10 to the 44. And in mathematically, the Fuchsia can be solved by diagonalizing the Hamiltonian matrix of this dimension. So in this case, we have to diagonalize the matrix of the dimension 10 to the 44 rows and 10 to the 44 columns. So it's impossible even to store this tremendously large matrix on the memory. So this is why the quantum mechanical calculation is so difficult in classical computers. However, this kind of quantum mechanical calculation can be efficiently performed by using quantum computers. I will show you the basic idea for this approach. As I said, the Fuchsia is intractable on classical computers because the number of variables increases exponentially against the system size. But because quantum computer can use the quantum superposition, so if we utilize quantum superposition, we can express all electronic configuration with an orb of qubits, where an orb is the number of spin orbitals. So it means if we prepare an orb of qubits, basically we can express, for example, Hartree-Fock or CCI, or so basically any kind of wave function can be expressed by using an orb of qubits. And also, quantum computer can use the projection measurement. So measurement projects to the some quantum space to the eigenstate of the observable. So if we can utilize this, this projection measurement, we can obtain eigenfunction or eigenvalue of Hamiltonian. This is the basic idea of quantum phase estimation. And also, if we can, because of the wave function of atomic molecules are entangled or correlated with quantum states, so if we can generate such correlated wave function by applying some kind of quantum circuit we can iteratively perform quantum state preparation and measurement. We can calculate the expectation value of Hamiltonian. This is the best idea of variation quantum eigensolver. But today I'm going to mainly focus on this, the former approach quantum phase estimation. But before explaining the mechanism of quantum phase estimation, I would like to show you the very simple comparison of QPE and VQE. Because quantum phase estimation uses the project measurement, we can obtain eigenvalues of the full CI or Cauchy with function. Cauchy is of the full CI within the selected set of molecular orbitals, which is called as active space. And by contrast, in VQE, we calculate the expectation value of unique couple cluster or more heuristic wave function, basically approximate wave function. However, the quantum search for QPE is very deep, so it is very difficult to perform QPE of large molecules in mixed devices. But the quantum search for VQE is very shallow, so we can treat large, larger molecules than the EQPE can treat. However, the computation cost, again, I will explain the detail, but the computation cost it will increase against the energy precision in quantum computers. And the computation cost gain is shown here. It means that if we want to make the energy precision to be half, the computation cost in QPE will become twice. But in VQE, the computation cost will increase progressively. And most important thing is in QPE, the exponential speed up against classical counterpart is guaranteed. However, in VQE, it is unknown. So it means no one knows if VQE can outperform the quantum, the classical calculation. But however, if we apply a QPE, because of the computation cost of QPE is polynomial, although the full CI in classical computer is exponential. So if we cross somewhere, so QPE is very promising if the fork train quantum computers are realized. And let me explain the basic principles of quantum phase estimation. Assume that we have a wave function, and we apply a time evolution operator to the wave function. If the wave function psi is an wave function of Hamiltonian age, it causes the phase shift depending on the energy. So it means if we can determine the phase shift caused by the time evolution, we can extract the energy eigenvalue of the system by using this equation. To realize this kind of approach, this is a quantum circuit for the simplest quantum phase estimation. I mean, the 1 qubit for energy return. As you can see, this quantum circuit is very simple. It contains 2 Agamal gates and 1 controlled time evolution operator. So Agamal gates generate the superposition on 0 and 1 state from 0 state, and then apply control time evolution. So it apply a time evolution operation to the wave function if the first qubit is in 1 state. And then apply another Agamal gate. could keep back the phase to the first QE and then measure the first QE. If the evolution time t equals 0, the measurement outcome is always 0 state. But if we apply a positive t, the phase shift, for example, for 90 degrees, in this case, the measurement outcome is 50-50 of the 0 and 1 stage. And if the time evolution causes the 180 degrees phase shift, the measurement outcome is always 1 stage. So the probability to obtain the 0 state in the measurement can be calculated by using this equation. Of course, in this case, the legal QB for legal is 1, but we can extend this kind of quantum phase estimation to n-cubic cases. And this is quantum 30 for n-cubic quantum phase estimation. In this case, the second abnormal gauge is replaced by inverse quantum phase quantum Fourier transformation. And apply control U and control U to the 2, U square, and U to the 4, and U to the 2n minus 1. Now, if we measure the quantum state, the measurement outcome corresponds to the number of decimal, number in decimal digit in binary. So we have to apply U, or U to be 2, or U to be 4. And this, why, for example, U square is introduced. It can be really easily understandable by considering the calculator, which can read only first decimal digit. So you have a calculator, but your calculator is somewhat broken, so you can read out only the first digit. So how to read out, for example, in the second digit? Of course, we can multiply 10 to move the decimal point. So in this case, we use the decimal, so we multiply 10. And in this case, we use a binary. So if we want to read out the second decimal unit, we have to multiply 2. And we want to read out the third decimal unit, we have to multiply 4, and so on. And this is a mechanism of n-cubic quantum phase estimation. If we apply n-cubic quantum phase estimation, if we read out the first decimal unit, this is 1, the Fourier energy is, again, phase is somewhere around this region. If we read the second decimal unit is 0, the Fourier, again, phase is somewhere in this region, and so on. So basically, the phase estimation algorithm doesn't calculate the energy itself, but the calculate the energy range where the Fourier solution located. And to make the energy range to be half, we have to make the evolution time twice to read another decimal digit. So this is the reason why the computational cost become double, but to read another decimal unit digit. This kind of n-cubic quantum phase estimation can be done by using single ancillary cubic by using the algebraic quantum phase estimation algorithm. In this case, there are another gate, quantum gate, DC, which is defined as shown here. So DC gate apply a phase shift if the quantum, if the cubic is in one state. In this case, we evaluate the least important visit. For example, if we want to read out the eigenphase with 10 decimal units, we have to apply first read out the 10th decimal unit with omega is 0. So it means that this, if omega is 0, this becomes just identity operator. So it doesn't cause anything. Next, we evaluate the next least important digit. For example, 9th decimal digit with omega equals 0. If the 10th decimal digit is 0 state, 0. But if the 10th decimal digit is 1, we have to apply minus pi over 2 rotation to the phase. And then next we evaluate the 8th digit. And the rotation angle will depend on the result of the 9th and 10th decimal digit. So basic idea is if the quantum scale after time evolution is somewhere around here, the probability to obtain 0 states is 50 and 1 state to be 50. But if we apply a back rotation, the probability becomes 100 0 or 1 state in this case. So, if the original quantum phase is on the positive imaginary axis, and then apply a minus pi over 2 rotation, the measurement outcome is over 0 states. This is the basic idea, or iterative phase estimation. Another approach based on the quantum phase estimation is based on the machine learning using Bayesian inference. In this case, again, we have another DC gauge we call phase rotation. And in this case, the time evolution and phase shift, which corresponds to the reverse time evolution. And the probability to obtain the 0 state in your measurement can be calculated in this equation. So the probability depends on the difference of eigenvalue and epsilon. And if E equals epsilon, the measurement always gave 0 states. So we can perform this quantum study with different epsilon value and plot the probability to observe 0 states. It becomes something like this, and we can fix this plot by using this kind of cosine function or Gaussian function. And peak of this cosine function gives the estimate of E. So basically, we can calculate the eigenphase by using the quantum phase estimation algorithm. But how long do we have to simulate the time evolution? The relationship between the evolution time and energy precision can be easily calculated. It depends on the, basically, I only use this equation. If we substitute t equal 1, the t, in this case, e equals 2 pi phi, and phi should be in the range between 0 and 1. Basically, in cubic quantum phase estimation, we can determine the eigenphase with an accuracy of 1 over 2 to the n. So it means if we use 1 cubic quantum phase estimation with evolution time t equals 1, we can calculate the energy with the precision pi. But if we increase the answer cubic or increase evolution time, we can decrease the energy precision. And if we want to achieve chemical precision, I mean the chemical precision means energy error less than 1 kilocalorie per mole. We have to apply 20 cubic quantum phase estimation with k equal 1. Well, if we use iterative quantum phase estimation, we need k is about 2,000. But if we use the Bayesian phase estimation, because the Bayesian phase estimation calculates the some kind of probability of the but not than the point estimate. So usually, if we apply a Bayesian phase estimation, we can need shorter evolution time. Of course, we have to, in order to apply quantum phase estimation, we have to map the wave function to the cubic. And the most simple one is direct mapping. In direct mapping, each cubic stores an occupation number of particular spin orbital. So cubic should be in one state if the spin orbital is occupied, and in zero state if the spin orbital is unoccupied. So, for example, this kind of Fock configuration can be represented by 11110000 states. If we consider this kind of Fourier expansion, and this state can be represented by 11101000 states. Expansion question equal to the question of this basic state. So basically we can map the wave function to the cubic, but we have to, the wave function should satisfy the anti-commutation fermionic nature. So that's why Jordan-Wigand transformation or some other transformation should be applied. And in Jordan-Wigand transformation, this kind of standard Hamiltonian should be transformed to a cubic Hamiltonian, which is composed by a Pyle string. And basically, because in the direct mapping, the zero state is unoccupied and one state is occupied. So maybe you can think, you can expect the go to this kind of operation can correspond to the equation operator. However, the some quantized equation initiation operator should satisfy this anti-commutation relation, which originates from the fermionic nature of electrons. So, actually, the equation operator can be represented by this kind of go to one part and another power 3 operators. So, for example, this one electron operator can be transformed to this kind of operator. Sorry, this is a Q plus, not plus, but minus. Of course, there are other mapping methods. In Bragg-Kitaev, one very famous approach is Bragg-Kitaev transformation. In this case, the cubic stores the parity which corresponds to the fermionic nature and occupation number non-locally. Another possible mapping method is practical superpower encoding. In this case, we assign the qubit to the not to the orbital, but the interaction terms shown here. If you can expect the practical superpower encoding need more qubits than the John Wigan or Brascaif. But in this case, both the parity and occupation can be stored locally on the qubit. So in this case, if we apply a practical superpower encoding, the number of qubits becomes larger, but the power string becomes shorter, basically. And this is a control strategy corresponding to the control time abolition operators. This is a very simple example. We have to apply analogy if the power x operator is applied. Apply 90-degree rotation to the 3 and 5, which power y is applied. And then apply a single ladder, and then apply RCJ. But in quantum phase estimation, we have to apply this kind of time evolution operator in controlled manner. And controlled time evolution operation can be realized by replacing the RCJ to the control RCJ. So the procedure for quantum phase estimation-based full can be summarized in this slide. We use the classical computer for preparation of Hagen-Fock calculation and 1 and 2 electron integrals, and apply Feynman cubic transformation to generate a cubic Hamiltonian. And then the result is transferred to the quantum computer. And in quantum computer, we have to prepare a approximate wave function on quantum computer and simulate the time evolution wave of the function and rig out the approximate energy. And this is the process of principal experiment, which is first, this is the first example reported in 2010 using the photonic quantum strategy. As you can see, this quantum strategy contains RCJ. So this simulation, this experiment uses the iterative quantum phase estimation algorithm. And they calculate the potential energy curve of hydrogen molecule. And this is a grand scale curve, and single aesthetic state, also single aesthetic state, and triple aesthetic state. Also, this kind of experiment was reported by using NMR quantum computers. In this case, the wave function is generated by using adiabatic algorithm. Another example is using the NV center of diamond to simulate the potential energy curve of helium hydride cation. So helium hydride cation has only 2 electrons, which is the same number of electrons as the hydrogen molecule. But the helium hydride cation, the 2 atoms are not equivalent. So it will break the spatial symmetry. So basically the calculation of helium hydride cation is difficult, more difficult than the hydrogen molecule. This is the computation time estimation. The computation time, of course, computation time depends on the error rate and the time for the single gate operation. Because the quantum strategy for quantum phase estimation is so deep, so we have to apply a error correcting code to obtain correct result. In this case, the structure 1 corresponds to 54 orbitals. So basically, we need 108 qubits to store the wave function. Now, if we apply a simple approach, this calculation can be executed within about half day, 12 days, if the error rate is something like that. But if we can use more qubits, more logical qubits, the computation time becomes shorter. Now, again, this is another estimation of computation time for phase estimation. In this case, the electron structure, you can, for example, 1,000 spin orbitals for Ci can be executed with the millions of physical qubits within about 14,000 hours. But of course, in the quantum mechanical calculations, we cannot have the eigenfunction before the calculation. If we already have the eigenfunction, we don't have to calculate. So we have to use approximate wave function for quantum phase estimation algorithm. If we use the approximate wave function, the result can be written as shown here. So this is the expansion question. And as you can see, in the measure which electron state can be obtained, is proportional to the square overlap between the CK, which is the which is square of the CK, which corresponds to the square overlap between the approximate wave function and the full Fourier wave function. So it means preparing good approximate wave function having sufficiently large overlap with the Fourier wave function is very important in the quantum phase estimation algorithm. If we use the Bayesian phase estimation, the situation becomes slightly changes. In this case, the probability to obtain the zero state in the measurement is written as in this equation. So the probability is proportional to the square overlap and this cosine function. So if we measure perform the quantum circuit shown here and obtain this kind of plot, we can estimate the result. But if the approximate wave function is poor, in this case, the target state have large overlap, but in this case, the contribution from many other electron states cannot be neglected. Contribution from the other electron state will shift the peak position from here to here. So if we use the poor approximate wave function in Bayesian QPE, which will shift the energy. But anyway, important thing is we have to prepare the good integral wave function having sufficient line overlap with the Fourier wave function. And usually in quantum phase estimation based Fourier, we assume two things. One is Hartree-Fock wave function is a good approximation of the ground state wave function. Unfortunately, this assumption is not always correct. Let's take the example is opposition molecule having spin beta electrons. In this case, the spin symmetric adaptive wave function is very important. Using spin symmetric adaptive wave function is very important. I will show you later. Another assumption is Hartree-Fock wave function is available. Unfortunately, sometimes Hartree-Fock calculation doesn't converge in large molecules like proteins. So application of quantum mechanical calculation on quantum pairs with such system where Hagen-Fock doesn't converge is still an open question. So we'll show you the simple example of which Hagen-Fock is not a good approximation. This is the potential energy curve of hydrogen molecule calculated using Hagen-Fock and Fuchs-I. And this is a broken simple UHF state. As you can see, Hagen-Fock method is a good approximation around its equilibrium geometry. But the situation becomes worse if the chemical bond is broken. So molecules undergoing bond dissociation are representative of opposite system. So we have to overcome such overlap catastrophes. Because if the fair overlap is exponentially small, even if the QPE can be executed exponentially faster than the classical counterpart, we have to execute quantum phase estimation exponential time to obtain the correct result. So this spoils the advantage of quantum speed up. So we have to generate good initial gateway function by using shallow quantum search. So this is an example of preparation of good approximate function. In this case, I focus on the opposition mode, which has spin big electrons. This is an example. We focus on this hydrogen cluster, 5 hydrogen cluster, because there are anti-ferromagnetic coupling between the nearby hydrogen atoms, so the approximate spin configuration can be written as up, down, up, down, up. But if we use this kind of determinant as an initial gateway function, and this is this horizontal line specifies the energy, and the vertical line specifies the overlap with the Fuchs-I wave function. In this case, the overlap with the Fuchs-I wave function is at most 0.2. Fuchs-I wave function is actually written as their combination of many configurations. So, but if we use the configuration state function, which is a symmetry adaptive.
Sugiaski, you have 5 to 6 minutes.
Okay.
More. Okay, so.
Okay.
I'm sorry. So at least you can use, try to.
Okay. So if we use the configuration state function, the overlap becomes larger. In this case, 4 times larger than the result from the single determinant case. So the situation becomes more significant if the number of electrons increases. Another approach is because in this case, I focus on the silky bond cleavage in acetylene and ethylene and ethane molecule. Again, the horizontal axis specifies the fair overlap with the Fuchs-I wave function. In this region, the Hagen-Fock is a good approximation. If the bond dissociates, the configuration function is a good approximation. But in the middle region, neither Hagen-Fock nor configuration function are good approximation. So we have to generate a good integral function for in this region. So this idea is use the dialectical character. The wave function, considering the wave function of hydrogen molecule, the gas state in equilibrium geometry can be written as 2-0 configuration. If the bond dissociates, the wave function can be written as a 2-0 minus 0-2 configuration. And basically, the wave function can be approximated by using this equation. And here, y is a dialectical character. That is a measure of opposition electron configuration. Actually, this dialectical character can be calculated from only the Hagen-Fock calculation, broken symmetry, spin and restricted Hagen-Fock calculation. So by using this is the occupation number of walls unoccupied natural orbital. So by evaluating this en room to calculate the dial of character, we can generate good integer wave function. And this is results. In this case, if we use the dialectic character to generate my confinement wave function, we can obtain good integer wave function around all regions. So finally, I would like to specify some of the anticipated application on VQE is to flip for the state preparation for the complex estimation. So in this case, I investigated this dihydrogen molecule reaction pathway using 10 molecular orbital which corresponds to 10 qubit simulation. In this case, in point E, the avoided forcing occurs. So in this case, the point E, the wave function cannot be well approximated with the Hagen-Fock wave function. In fact, the sphere overlap is just 0.52. And if we apply conventional unitary coupled clusters using VQE, it doesn't converge even after 10,000 of iterations. Energy is still high and sphere overlap is less than 0.8. But if we use conventional wave function, the sphere overlap is already 0.9. So two conventional wave function prepared by using dialectic character have larger overlap with the fluxual wave function from the conventional unitary coupled cluster. So I have no time to explain the recent results, but if we use the quantum computers, we can calculate the energy gap directly. For example, in the ionization energy calculation, we have to calculate the total energy of neutral and ionized states and evaluate the difference. But because the quantum computer can utilize the quantum superposition, it means if we can generate the quantum superposition of neutral and cationic states, for example, we can directly calculate the different energy difference of two electron states, in this case, the ionization energy, without evaluating the total energy of individual states. So let me summarize my talk. The computation time on full slide on classical computers scale exponentially. But if we use a quantum phase estimation, it becomes polynomial scaling. And also, quantum phase estimation has several variants. I mean, the conventional n-qubit QPE, iterative QPE, and Bayesian phase estimation, and so on. And quantum 34 QPE so deep, so only small molecule like hydrogen molecule or helium hydride cation can be treated by using these devices. But because of the exponential speed up is guaranteed, so if the Fock-Toyan quantum computer is realized, it becomes a very powerful tool to calculate the electron states. But we have to generate good integer wave function having sufficient overlap with the fluxual wave function. Hagen-Fock wave function is usually regarded as a good approximation of the ground state wave function, but this assumption doesn't hold for opposition model having ample electron of spin beta. But if we can generate confidential state function or much confidential wave function, this problem can be solved. Because the time is over, so thank you very much for your kind attention.
Thank you very much, Professor Sugiaski, for a nice, very detailed talk about the many electron wave functions. I think that there will be a lot of questions coming up from the audience. Please ask questions. First, I would like to request all the participants to ask questions. You can unmute yourselves and ask questions, or you can write them in the chat box. You can simply unmute yourself and ask questions. students? So, is there any questions?
I have a question.
Yes.
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 Dr. Sugiaski, I was intrigued by this exponential minus ET, and since it is equal to e to the power minus 2 pi 5.
Yes.
So there is certain Fourier transform built in, isn't it? That's
Yes, exactly. Exactly.
So that's what you call a quantum Fourier
transformation.
Okay. So that's what would, but it's not clear as to how I would conclude that I have done one circle. You know, you said you go 1 quadrant, 2 quadrant, 3 quadrant.
Yes, yes, yes.
And then you said you go back 1 quadrant, that brings you the accuracy.
Yeah, exactly.
Yeah, right.
Of course, we can obtain same result if the one, in this case, this and this one and this one or something. But in this case, we can expand n-cubic quantum expansion with u, square root u, or u to the 1/2, or u to the 1/4, or anything, to rigor the first and second decimal unit. So basically, we can calculate the total phase.
So
in this case, basically, the quantum phase expansion, this quantum phase expansion algorithm can rigor only the first decimal unit digit. So if we multiply 2, we can rigor second decimal unit. If we multiply 1/2, we can rigor in this case 0 state, and so on.
So we typically do a calculation. Many of the calculations are good enough to a micro heart tree. You know, that's the kind of a convergence we set in. So a micro heart tree would correspond to 6 decimal places. So do I understand that that means I break it into 6 segments?
Well, in micro heart tree case, it's the 6 decimal unit. But in quantum phase, quantum computer uses binary.
Okay.
So the number of digits will increase.
Okay. Okay. So instead of a base 10, it is a base 2. Okay. Yeah.
Yes.
Okay. That's all right. That can be worked out. Sure. Thank you.
Thank you, Professor Timothy. Anyone else who want to ask Dr. Sugiaski? Actually, I have one question to ask you. Yes. Given the qubit we have right now, so what is the maximum number of orbitals you can calculate for the full CI? Because you want to do a full CI calculation, and the maximum number of orbitals that can be doable in qubit, because you already know that it's taking too much of time to do full CI calculations.
So you mean using real quantum devices?
Yes.
Well, in this case, it depends on the size of molecule.
Okay. Yeah, I'm saying this. Suppose any molecule people have tested it. That is a maximum molecule that can give you the full CI calculations, number of orbitals. Compared to classical computers.
Well, to the best of my knowledge, only few examples have been reported using real quantum devices, like shown here. This is a hydrogen molecule and hydrogen molecule and helium hydride. For volatile systems, the functionality for time evolution becomes so deep, so it's quite difficult to obtain meaningful results using the NIST devices because the error rate become very high. So ODE measurement outcome become just random. So we cannot evaluate the correct energy. So this is a major difficult point of QPE.
Okay, thank you very much. So if Professor Panigrahi, do you have to ask some questions?
No, I am.
Okay.
I noted. I just wanted to thank Professor Sugiaski.
Yeah. Thank you. So please join me in thanking for a nice talk. Well,
thank you very much.
Thank you. So now I handed over the session to Professor Panigrahi for the next speaker.
Thank you, Mosumi. And
you're welcome, sir.
It is actually Ashwini now. It is Ashwini. Are you around?
Yeah, I'm around here.
Yeah.
So
Nitik is ready.
Nitik is ready. So Nitik, you share your PPT file here. Nitik, are you there? Hello.
Yeah, he is there. Just I'm looking for him.
Yes, sir, I'm here.
Do you please share your PPT? Yeah. So let me introduce Nitik. So Nitik basically did PhD from the Calcutta University with Professor Kamal Bhattacharya, and then he moved to IISER Kolkata. He first joined as a postdoc with Dr. Amral Kusum Rai, and then he went on doing as a national. He got national postdoctoral fellowship, and now he's a CSIR pool officer in the same group. And Nitin research basically focus on the information entropy measurements on the many most of chemicals for the chemical systems. And I know his research because I was involved many of the interview he faced. So he basically used many like Rayleigh entropy and all these entropic measurements to understand the chemical system. So with this introduction, I invite Nitik to present his lecture. Nitik, yes, please. Hello.
Hello, sir. Thank you, Professor Tiwari, for your support. And first of all, before start, I should acknowledge QIQT and Professor P.K. Panigrahi for giving me this opportunity to present our work in this prestigious symposium. So today our topic is the confined quantum system and information entropy in chemistry. Actually, in our laboratory, we have designed a DFT-based method to study confined quantum system for both in one electron system and also in many electron system. In this talk, my focus will be on one electron system, that means for hydrogen-like atom, and how information entropy has helped in our calculations. And in today's last talk, Dr. Shongita Majumdar will present how the method we are using, the DFT-based method we are using, and also the many electron results. The structure of my talk is that, first of all, we'll discuss what quantum confinement is, and in the context of hydrogen atom, how it impacts. Then we will proceed we have found a Virial-like theorem for this confined quantum system, and we'll discuss dipole polarizability. Then finally, we will move to information theory, and we'll discuss some of our findings in double wave potential and in confined hydrogen atom. Now, what is quantum confinement? In this, it should be in this context, I should mention early that in the confinement we are discussing is of atomic scale, and this, in general, quantum confinement means trapping of an atom inside a finite region. And due to this trapping, especially the electric and optical properties of the material changes. If you see the figure in the right hand side and move move from left to right, then we can see that the wavelength increases, and it results as that the color changes from blue to red. Now, if some of the practical example of quantum confinement is the encapsulation of atom inside a spherical cavity, or encapsulation of a molecule inside spherical cavity, or maybe in cylindrical nanotube. Depending upon the confinement or confined environment, confinement can be classified into 4 different parts. First, the impenetrable sharp confinement. What does it mean? If you see this figure, then it says that the particle is confined inside a infinite box, and the first and foremost example of such condition is the particle inside extreme pressure, and this high pressure situation has led us to a new field of chemistry, that high pressure spectroscopy. Next, we move to the impenetrable smooth condition. In this condition, the boundary is obviously infinite, but it's in continuous nature. The example is that the harmonium trapping of an atom inside an harmonium environment. Next is the penetrable sharp. In this condition, what we can see that the particle is trapped inside a box, but the box boundary is finite. And next, the trapping of atom inside a supramolecular cavity like fullerene or zeolite, and we classified this as a penetrable smooth confinement. And so far, this is now, apart from that, we can see that quantum confinement has its application in nanoscience and nanotechnology. So as I have said before, that in this talk, I will discuss specially on hydrogen atom. So the Schrodinger equation for respective hydrogen atom is of this form. And here VR is the confinement potential. If you see this, the expression of VR, then and see this figure, then it says that particle is trapped inside a ring having inner radius RA and outer radius RB. And if with outer radius RB, if we think that RA is 0 and RB is finite, we get a confined hydrogen atom. Then if our RA is 0 and RB is infinite, then it leads to a free hydrogen atom. And if both RA and RB is finite, then it leads to a new model called shell confinement, confined hydrogen atom. Confined hydrogen atom is one of the 2-3 prototypical systems that can be solved exactly. And this is the solution of confined hydrogen atom. But there is a but, because this solution is of transcendental type, because we can see that beta is a function of energy. So to get the function R rho, we need to get the information of energy. But the point is that without getting then before to get the exact function, we need to calculate the energy. That means without the information of energy, we cannot proceed. And second, and again, there's another special characteristics of it. If our RC goes to infinity, then this function modifies to associate logarithm polynomial, which is actually the solution of free hydrogen atom. Now, as we are discussing about the wave function and energy, it should be mentioned that in confined condition, the energy of an hydrogen atom changes drastically. The first example is that in a free hydrogen atom, the energy is expressed in the form of z square by 2 minus z square by 2n square. That means energy is only dependent on its principal quantum number. But in case of confined hydrogen atom, it depends on both principal quantum number and orbital angular momentum quantum number. That means both on L and N. Secondly, the presence of accidental degeneracy, that 2s, 2p state are degenerate. Similarly, similarly 3s, 3p, 3d, these states are degenerate in hydrogen atom. But this degeneracy is lifted in confinement condition. Third, if we see that the kinetic energy of hydrogen atom, then we can see it is of the form of z square by n square, and we can see that with increase of n, kinetic energy of a given state decreases. However, it can be seen that in confined condition, kinetic energy of a given state increases with increase in n. And now, if we analyze the energy levels of confined hydrogen atom, then we can see that 2p, the energy 2s state have higher energy compared to 2p state, as well as the more interesting, that 3d state. Similarly, 3p state have higher energy compared to 4f state. So the interesting part is that we can see that due to this confinement, rearrangement of atomic orbital occurs. And this rearrangement of atomic orbital is responsible for changing the properties in confined quantum system. And the primary effect is that due to this rearrangement of atomic orbital, the coordination number of an atom changes, leading to changing in its valency and bonding characters. Now, if we move to from hydrogen atom to shell confined hydrogen atom, that means instead of choosing RA0 and RV is finite, we are choosing both RA and RV finite. That means particle is trapped inside a ring. This situation is a mimic of encapsulation of an atom inside Fullerene cavity or zeolite cage. Like to be specific, in a supramolecular cavity, we can use such type of model. And it has been found that in such model, some interesting incidental degeneracy exists. And that degeneracy is completely dependent on the nodal position of the free hydrogenic state. Suppose we have a free NL state. For example, we can take 4F state. For example, we take 4S state. That means including if we consider 0 and infinity including it, then it has 3 node plus 0 plus infinity. So if we place let A, B, and C, it's 3 nodes. If we place our boundary, if we choose RA equal to 0 and RB is A, then its energy is same with the free hydrogenic 4F energy. Similarly, from A to B, it will have the same energy of the one state has the same energy with the 4S state. Similarly, if we choose 0 to B, then this state has a node at A. Then it is representing the 2S state, and these 2S states again have the same energy with the 4S state. That means just placing the boundary at the point of node, we can extract isoenergic state of SCH state. This is the interesting part of incidental degeneracy that arises in shell confined condition. Similarly, another type of degeneracy arises that's called simultaneous degeneracy. For if our n, free n is free n, if a higher n has n, if the lower state L plus 2 value is less than the higher n state, then we will get degeneracy, and corresponding length of the box can also be defined obeying this formula. So from this discussion, we can say that a fascinating change in energy distribution, in energy, has occurred if we move from a free to confinement, and depending upon the confined environment, this properties changes. Now we move to the Virial-like theorem. We know that the famous Virial theorem, that twice of the average of kinetic energy is equal to the R into dV/dr, expectation value of R into dV/dr, and this is a necessary condition for a bound stationary state to obey. But unfortunately, for confined quantum system, this relation is not obeyed. Particularly in the slide we have seen before, particularly in the first and third case, this relation is cannot be used. Even for second and fourth state, with some small modification, we can use it, but for first and third state, we cannot use it. So in this context, we have designed a Virial-like theorem for confined quantum system, and it says that the standard deviation of kinetic energy is exactly equal to the standard deviation of kinetic energy, and they have the common form of product of the kinetic and potential energy, expectation value of kinetic potential energy, and also the expectation value of their product. Not only the Virial-like, not only satisfy the Virial-like condition, the interesting part of is it can act as a sufficient condition for both free and confined, in both free and confined situations. And if the proof is that if we use a famous Hendekovich variation principle, that delta H is for an eigenstate, delta H squared, or the standard deviation of Hamiltonian is standard deviation of total energy is exactly 0. So, and if we replace this expression, if we use, and it has a form of this, and if we use this, the above expression in it, then it leads to this form. That means that proves that this first form of equation is a sufficient condition. And moreover, another interesting thing that connected to Hendekovich variation principle also in this case is that in this case, in usual variation principle, we get the lower bound to the ground state energy, and after applying the orthogonality constant, we can calculate the excited state energy. But in this case, without using the orthogonality constant, just using the appropriate nodal information, or just using the appropriate information, we can extract the energy of the excited state. So from this discussion, what we can conclude that we have designed a general Virial-like theorem for confined quantum system, and this condition is obeyed for all obeyed by all non-relativistic system. And further, it can be used for optimizing and wave function. We have not used it, but it can be used. And another important thing is that if we use the first and third condition, then the effective expression of the Virial theorem does not change, because in both of the cases, the confinement is applied in terms of a constant barrier. However, in second and fourth state, we have applied perturbation in terms of perturbation or confinement in terms of some potential function. As a consequence, this will influence the expression. Now we'll move to the dipole polarizability calculation for this confined quantum system. We know that in a system, in presence of some external field, the electron cloud distort. So this is polarizability is a power of this distortion of electron cloud. So in this case, this is the expression. This F is called the oscillator strength, and this is the contribution from the continuum state, and alpha contain the contribution from both bound and continuum state. EI is the initial state for which we are calculating the dipole polarizability, and En is corresponding the other state in which the transition occurs. And usually for dipole transition, the selection rule is ±1. Here we are doing it for the hydrogen, and sorry, one state we have shown here, so the selection rule modifies to +1. And these are the expression for the dipole oscillator strength. And finally, for these the dipole oscillator strength, they needs to obey this dipole sum rule. Now, in free hydrogen atom, this dipole polarizability can be computed exactly. And in this, this is the expression. And from this expression, it's clear that dipole polarizability of a given state of a given NL state of hydrogen atom increases with increase of both N as well as L quantum number. But what happens in confined hydrogen atom? Let's see. If we choose RC equal to 1, then you can clearly see that from 1s to 10s, dipole polarizability gradually decreases. That means, and it's in the right-hand side of this table, we can see the results of FHA. So if we see the second and fifth column and just compare it, And you can see that here dipole polarizability decreases, whereas here dipole polarizability increases with increase of n. So that means exactly opposite behavior is seen here. That means that in free condition, higher quantum number states are easy to polarize. However, in confined condition, higher quantum number states are difficult to polarize. That the reason behind is that in free condition, we know that the wave function with increase of quantum number, wave function gets diffuses. That means wave function gets diffused. So, but however, in confined condition, all these states experience the same boundary. So as a consequence, and that boundary is that the wave function must vanish at r equal to 1. As a consequence, the impact of confinement on higher quantum number states is more. So they are more localized, and as a consequence, they have lower value of dipole polarizability. Now we move to other two cases where we can see that at RC equal to 5, dipole polarizability initially decreases, then again it increases, and if RC equal to 17, then it's for in the 5 case it was 2s state where the polarizability was initially from 1s to 2s it was decreasing, then again it was increasing. However, for RC equal to 17, we can see that from initially for 1s 2s state it increases. However, for 3s state it decreases. That means from it's very clear that if we move from free to confined, that means if we start relaxing the boundary condition, then it can be seen that to modify this pattern to this pattern, they go through this. As a consequence, this zigzag pattern is seen. Another point is that here we can see in R5 and 17 negative value of polarizability. This is quite interesting because this happens because we know that in a dipole transition, in case of in dipole, the selection rule is plus 1. So transition occurs from 2s to 2p state also, and we have seen that for confined condition, 2s states have higher energy compared to 2p state. So in excited state, not in ground state, in excited state, dipole these have we have in dipole in excited state dipole polarizability. There are contribution from both absorption and emission. As a consequence, we get if the contribution of emission is higher, we get the negative value of polarizability. That's why for higher states we get negative value of polarizability. However, in free condition, due to presence of accidental degeneracy, this never arises because we know that 2p and 2s states are degenerate, and then 3s states have higher energy compared to 3p states have higher energy compared to 2s states. So as a consequence, only absorption occurs, and we get positive value of energy. So from this we can conclude that from free to confined condition, several fundamental physical as well as optical properties and spectroscopic properties of the system changes drastically. Now we move to discuss the importance of Shannon entropy in this confined condition and how Shannon entropy helps us to explain several phenomena in confined environment. Now, to begin with, I can say that what are the primary application of quantum information in chemistry? First, we start with the uncertainty principle. We know that the famous Heisenberg uncertainty principle, what it says that we cannot measure simultaneously the position and momentum of a particle. We cannot measure simultaneously accurately the position and momentum of a particle. But in that case, what we see that they are just the product of their standard deviation. As a consequence, only the second order correction has been taken. But in this expression that SR plus SP, where SR is the Shannon entropy in position space and SP is the Shannon entropy in momentum space, it says that and it's d times, this is the dimension, d times 1 plus ln pi, and arguably this is the best uncertainty expression we have reported till date. I have not derived this relation, but it can be derived, and and if you have interest, please. So then I can share the manuscript where these are derived. It was derived in 1971. Also in 2003, this was modified in a famous physical review way by Virial-like in there. So this is so uncertainty principle has been deeply influenced by quantum information. The second point is that the effect of quantum information on density functional theory, which is our point of interest. We can, in an orbital, the Euler equation in orbital free density functional theory can be formulated by Shannon and Fisher information. Apart from that, in Fukui function has a first derivative with respect to n, and that is directly related to Shannon entropy. Another case is that in chemical reactions, Shannon entropy has been used in explaining several chemical features like steric effect, internal rotation, aromaticity, localization, delocalization problem, rate of a chemical reaction, etc. Further, we have seen that in quantum confinement, quantum information had used and can explain many phenomena that cannot be explained by so-called uncertainty principles. Next is that the famous entanglement problem. Now we move to discuss what is this information measure is. So before discussing that, I just want to point out that these information measures are just the function, are mainly the functional of density, and they can quantify density. As a consequence, they have immense importance in chemistry. Now I discuss what is this Shannon entropy, these information measures. Especially we'll discuss about Shannon entropy, then Renyi entropy, Fisher information, and Onigescu energy. Shannon entropy is a measure of information, and what is information is that if before the amount of uncertainty, if you see this expression, the amount of uncertainty prefers before the occurrence of an event, then after occurrence of the event, the exactly equal amount of information is received. And Shannon entropy is the arithmetic mean of information, and it becomes maximum for an equiprobable distribution, and it's minimum for a certain event having probability 1. And the Shannon entropy has this mathematical form, and so far, and Shannon entropy arguably the best descriptor of localization and delocalization. Now we move to Renyi entropy. Renyi entropy says that Renyi entropy is a geometric mean of information, and more interestingly, when the power alpha of Renyi entropy and also the power of beta in Renyi, and also the power of beta reduces to 1, there actually this alpha beta follows this relation, reduces, if both are 1, then its Renyi entropy reduces to Shannon entropy, the special case. But though it seems that the Shannon entropy is a special case of Renyi entropy, and Renyi entropy is more general, but effectively Shannon entropy describes the uncertainty more general way, more profoundly. So now we move to the Onigescu energy. What it is? It's a measure of disequilibrium. In general, you can say this is the exactly opposite of Shannon entropy's behavior is exactly opposite of Shannon entropy, because it's maximum at disequilibrium and it's become 0 at equiprobable distribution. In a different way, it's actually complements Shannon entropy, and it's actually the expectation value of density. Now we move to Fisher information. What Fisher information says? Fisher information actually determines the expected error in a smart measurement. In our sense, it measures the fluctuation of a given density distribution, and for a sharp, it's high for a sharp distribution, and however it's small or lower for a flat distribution, and it's actually have the expression of this. Now we move to the statistical complexity. What it is actually, statistical complexity is a derived quantity. We know that the like Shannon and Onichescu energy shows complementary behavior, or they have reverse behavior. Similarly, in sometimes Shannon and Fisher also show inverse behavior, and depending upon these conditions, there are certain parameters are designed which can explain system better, and their behavior may vary depending upon the situation. Usually, three types of pattern is recorded. One is that these are the complexities. I'm just discussing their property after saying this, that if we have a Onichescu Renyi entropy, then Onichescu appear in P exponential factor, and any entropy appears in exponential factor. Always the information part, that means the Shannon or Renyi entropy part, appears in the exponential part, and the Onichescu energy or Fisher appears in the pre-exponential part. And these be a certain parametric constant that has been derived. So depending upon the situation, we can get three types of patterns. First is that the advances monotonically with disorder. If you see, this is the right hand side as the order of the disordered axis, then we can see that complexity increases with increase of disorder. Similarly, there are situations where we can see that complexity decreases with disorder, and also there are reported cases where the complexity initially increases, attains a plateau, and then falls off. So with this knowledge, now we proceed to see and explain some of the examples that we have studied in our laboratory, and see how how these information measures and influence in our calculation. First of all, we start with the double L potential, the famous model that in chemistry it's directly related to the umbrella flipping of ammonia, and this is the generalized expression of double L potential. This is, if we put gamma equal to 0, then it reduces to symmetric double L potential, and if gamma is finite, then positive finite number, then it reduces to asymmetric double L potential. And in symmetric one, both the well are same, and well, as a consequence, well depth are same. Wherever in this condition, we have shown the figure for asymmetric condition, and it's seen that it seems that they have a shallow well and one deeper well. Another point is that if we consider a double well potential, then probability of finding the particle in either of the well is same. However, for asymmetric double well potential, we can see that at certain parameters at which you have choose alpha equal to 1, beta 10, then the odd state resides in a deeper well, and the even state resides in a shallower well. Similarly, if with increase of quantum number, there are situations when there are states when their probability of finding the particle in higher excited state in either of the well is more or less similar, not exact, because there are difference in their well depth. So this is the description of a double well potential. Now we move to study the information entropy for this symmetric double well first. That means we're choosing gamma equal to 0. And in this case, we have initially tried with the conventional uncertainty principle that delta X and their product delta P, and study delta and C, that in both delta X and delta P increases with increase of beta. So the competing nature that exists in a double well potential due to this alpha and symmetric double well potential due to this alpha and beta is not understood, because alpha actually is directly connected to this alpha beta actually directly controls the localization delocalization phenomena in a double well potential, and depending upon their values, the probability where it is depending upon their value, it's completely controlled, and as a consequence, the quasi degeneracy arises. That means the pair of states becoming very close, though they are not degenerate, but they are becoming very close to each other. Almost they have same energy up to 8-10 digits. But again, as we are studying a one dimension, so then degeneracy cannot exist. So we call it as quasi-degeneracy. And now from this plot, we can see that for start with the ground and fast excited state, that initially Shannon entropy increases, then it attains a maximum and then falls off. So as we know that in Shannon entropy, we have to, in calculating the Shannon entropy in position space, we need to use a wave function. Similarly, in momentum space, we need to use the momentum space wave function. But in a conventional uncertainty principle, taking the information of either of the space or either from the position space wave function or momentum space wave function, we can calculate the both. But here we have to calculate the Shannon entropy in position space. Sx is calculated in position space, Sp is calculated in momentum space, and their sum is expressed in plot, and they obey the uncertainty relation that given before in this expression. Now from this, what we see as this appearance of this maxima, what he says, that means initially with increase of beta value, these are plotted against beta, keeping alpha equal to constant equal to 1. We've seen that initially with increase of beta, delocalization increases as a Shannon entropy increases. So as a consequence, delocalization increases. And then it attains a maximum. Hello,
you finish in 5 minutes, so that you have another 5 minutes for discussion. You're talking for 45 minutes total.
Okay, sir. So this appearance of maxima indicates that the competing nature of alpha and beta has been explained using Shannon entropy, which was not done before. Again, we move to asymmetric double well, and we see that the probability particle reside either deeper well and shallower well. And from this peak, from this certain jump, we can see that these are actually indicates the oscillation of the particle from shallower to deeper or deeper to shallower well. And this again can be explained by Shannon entropy. Now we move to confined hydrogen atom, and these are the results for the some selected RC values for confined hydrogen atom at 2s and 1s and 2s state. From these we can see that 2s states has lower Shannon entropy compared to 1s state. This again that due to the fact that higher excited state experience greater impact of confinement than the position space. So from this, we can conclude that the confinement region, hard confinement condition, strong condition, the particles show exactly opposite behavior compared to its free counterpart, and moderate confinement, due to the transition from free to confinement, due to the relaxation of confinement, their behavior changes. So now we move to another problem that we have done for compound profile. We have studied the effect of confinement and compound profile for some low line state at selected RC values, and from these we can see. And further, we have analyzed this compound profile, the area of the compound profile, to understand the rate of dissipation of kinetic energy that using Shannon entropy, and we see that for 1s state, it has lower value of Shannon entropy compared to the higher state. That means the rate of dissipation is higher for higher state. So now we move to determine the critical screening constant of plasma system. That in this case we have used Shannon entropy to understand a critical screening constant. Usually what happens that in plasma system, there exists finite number of bound states, and there is a characteristic value of lambda at which a particular state gets deleted, or that state become continuum. So usually energy sign change argument use. That means when energy become negative to positive, then we determine that point as a point of transition for critical screening constant. But in this case, instead of using energy, we have used Shannon entropy, because usually here what is happening, I have said that the state become from bound to free, so the Shannon entropy should increase, and we have applied Shannon entropy at that point to determine this point, and we see that at that point of transition or that critical point, Shannon entropy increases stiffly. And from these, and these has been done for several Z values and for 1s, 2p, 2p and 3p states. And from these results, it can be concluded that Shannon entropy can be used as a very good descriptor in explaining the critical screening parameters of plasma system. And these are some of the results we have computed using Shannon entropy, and these results are exactly in very good agreement with the results we have, the results reported before in the literature. So from these, what so far we have some of the points I will summarize, that in confined condition, particles show several fascination and remarkable change in the physical and chemical properties from their free counterpart. These occurs due to the rearrangement of atomic orbitals, particularly, and then the Virial theorem is designed, which is applicable not only in confined condition but in both free and confined condition, and can be used as a for optimizing an eigenfunction. Again, so dipole polarizability is used again. It again shows that a strong confinement region, exactly opposite behavior is shown, which has again been seen in studying the Shannon entropy. So Shannon entropy, and further these has been used for double well potential. So, and also for critical screening constant. So thank you all, and I would also thank UIQT for giving me this opportunity, and also Professor P.K. Panigrahi for giving us the opportunity, and thanks Professor Ashwini Tiwari for that nice introduction, and IJAR Kolkata for giving me to work here, and CSR India for my research fellowship. Thank you all. If you have, sir.
There are questions in the chat box, so you can take those questions first.
Okay, sir.
You can read the, should I read for you?
No, sir, I'm checking.
Yep.
So these are the results.
Ritik, are there any other?
Sir, actually, hello. Hello.
Yeah, Nitik.
Sir, Aniket Kashyap has asked 2 questions, but I think I have to check. So I will check these answers, and if you ask, then I will answer, because these are not that quantum chromodynamics, and so I will check and I will answer.
Okay, so there is a question from Deven Tiwari, so you can look into that question. Yeah.
Oh, no. Okay, sir, the quantum confinement theory is, yes, quantum confinement can be applied to any quantum, the hydrogen, you can apply for a hydrogen atom, you can apply for a many electron system, the atom, molecule.
Check about the nature of the
in the last talk, Dr. Shongita will discuss about the confinement in helium atom. So,
sir, I have a question. Can I ask?
Okay.
Sir, you said that for confined hydrogen atom, the dipole polarizability depends as the principal quantum number increases. So more diffusion occurs. That. But sir, can I conclude, sir, it's a very rough conclusion. Sir, can I conclude that it is only applicable for n, if n increases, classical nature as well increases?
No.
Sir, does it, are we going from quantum particles to classical systems like this?
No, but the quantum classical correspondence in quantum mechanics is for higher end state, but these are ground or fast and very low line states. So not, it's actually this opposite behavior is seen because when you increase in a free system, if you plot your radial distribution function, then you can see the way the function gets diffused with increase of quantum number. So it's easy, these are easier to polarize. So that's the reason that with increase of n, the quantum number, the dipole polarizability increases.
Thank you, sir.
Okay, so Narshima essay told me that can you please elaborate on uncertainty and Shannon entropy? Actually, Shannon entropy is a measure of information, and we can information is directly connected to uncertainty. So to that extent, we can say that the Shannon entropy is the arithmetic mean of uncertainty, the base possible measure of uncertainty. So that's a point.
So is there any other question? If not, let us thank Nitin for a very nice presentation.
Yeah, Ashwini, I have a small question.
Okay. Okay.
See, Professor Satyamurthy pointed out in the morning that he has also used this information entropy to find that when it reaches maximum, the chemical reaction stops. Can you sort of connect your result with Professor Satyamurthy's result?
Sir, actually, when Shannon entropy become maximum, the distribution become equiprobable. So, so
maybe that is, you can take a look at his paper, because that sounds like there is some kind of deep connection, no?
See, yes, sir. I will definitely see, sir. Yes.
Yeah.
Okay, thank you.
Okay, thank you. Yeah.
Now we will take a break for 10 minutes, and then we will start the Susanto Mahapatra talk at 5 o'clock.